Hello everyone, I welcome you all to Startup Academy, your online gateway to get success in ISS exam. This academy is exclusively for ISS only. We have been covering the topic time series, and in today's lecture, we'll start with a new topic, spectral density function of a time series. So now, what is spectral density function of a time series? If we talk about spectral density function, then we can say that spectral density function is the Fourier transformation of the autocorrelation function of a time series. Now I have told you what is a Fourier time series. Fourier transformation means converting a time series into the sum of sines and cosines. This we have discussed in detail in the chapter in the topic correlogram. If you haven't previously seen it, then you can just go back to some previous lecture and see the correlogram one. And this is the Fourier spectral density function is the Fourier transformation of our autocorrelation function. So if we have, let gamma h be the autocovariance function of time series xt, then the spectral density function, I am writing it as SDF of xt, which is the time series, is defined as f lambda equals to 1 upon 2 pi summation h goes from minus infinity to plus infinity e raised to the power minus I h lambda gamma h. This is our spectral density function, where lambda lies between minus pi to plus pi, or minus infinity to plus infinity. These are the values range of lambda. So now there are some properties of lambda or spectral density function. That properties of spectral, I'm just writing it, spectral density function. So the first property is f lambda is an even function. What does this means? That f lambda is equals to f minus lambda. Okay. Then the second one is that f lambda is always greater than 0 for all lambda. F lambda is always greater than equal to 0 for all lambda which belongs to minus pi to pi. And the third property says that this autocovariance function can be defined as minus pi to pi e raised to the power I h t h lambda e raised to the power I h lambda f lambda d lambda, or we can also write this as minus pi to pi cos h lambda, f lambda, d lambda. So these are the three main properties that we will be using in the further derivations of our spectral density function. Now there can be many spectral density functions. The first one is white noise. White noise is let us say that we have a time series distribution of white noise where the time series xt belongs to white noise is white noise with mean 0 and variance sigma square. Okay, now the we know that gamma h for white noise gamma 0 would be equal to 1 sigma square. Gamma 0 would be equal to sigma square and gamma h equals to 0 where for all h greater than 0. Okay, so our spectral density functions formula is f lambda equals to 1 upon 2 pi. We can write this as gamma 0 plus summation 2 summation h goes from 1 to infinity gamma h into e raised to the power I h lambda. Now gamma h equals to 0, so this whole terms becomes 0 and we are only left with gamma 0, which is nothing but f lambda equals to sigma square by 2 pi. So this is our spectral density function of a white noise, and if we draw it on a graph which represents the values of lambdas on the x-axis and the spectral density function on the y-axis, then we can say that if this is sigma square upon 2 pi value, then the graph goes like this. So this is the graph of white noise, spectral density function of the white noise. Okay, now these values, this and this we have done previously in the derivation of our auto covariance function. If you haven't seen that video, then you can recheck that video. Then moving on further to our second AR1 model. Okay, we know that AR1 model can be given as xt equals to phi x t minus 1 plus wt, where all wt's are white noise and belongs to mean 0 and variance sigma square. Okay, now previously we have done this, that xt can be written as summation of j goes from 0 to infinity phi j w t minus t. And when we expanded this, when we found out the covariance, it was covariance between x t plus h and xt. If we open this bracket, then it will be I can write covariance as this as well, estimation of x t plus h. X t plus h can be written as phi t plus h summation j goes from 0 to infinity phi j w t plus h minus j. This is the first bracket, and summation k goes from 0 to infinity phi k w t minus k. And if we open this bracket, we'll be getting our answer as phi h upon 1 minus phi square into sigma square. This was our derivation for autocovariance function of autoregressive series of order 1. Okay. Now here we have to find phi naught. We can write the derivation of spectral density function. We know that spectral density function can be written as 1 upon 2 pi summation of h goes from minus infinity to infinity e raised to the power minus I h lambda f lambda, sorry, gamma lambda. Now this can be written as 1 upon 2 pi bracket open gamma naught plus summation h goes from 1 to infinity e raised to the power I h lambda plus e raised to the power minus I h lambda into phi h. This can be written like this. Now keeping the values of phi naught and phi h, we know that if we take the value phi naught here, then we will get sigma square upon 1 minus phi square. Then we can put the value directly here. We will be getting 1 by 2 pi sigma square 1 minus phi square plus summation h goes from 1 to infinity e raised to the power I h lambda plus e raised to the power minus I h lambda into phi raised to the power h upon 1 minus phi square. Now taking the common terms outside, sigma square will also be multiplied here. We will be getting sigma square upon 2 pi 1 minus phi square bracket 1 plus summation h goes from 1 to infinity e raised to the power I h lambda phi h plus summation h goes from 1 to infinity e raised to the power minus I h lambda phi h. And when we solve this bracket, we will be getting f lambda equals to sigma square upon 2 pi 1 minus phi square into 1 minus phi square upon 1 plus phi square minus 2 phi 1 plus phi square minus 2 phi cos h cos lambda. This phi square and this phi square will get cancelled, and we are only left with fh sigma square up. We can write this as 1 upon 2 pi sigma square upon 1 plus phi square minus 2 phi cos lambda. So this will be our spectral density function of our autoregressive series of order 1, AR1, and hence this is our final answer. I hope that whatever I have taught you about spectral density is clear with every concept, and I have tried to explain in details all the minimal concepts that has to be explained. If you are not clear with with the exam with the details that I have given to you, then you can recheck the previous lectures. I have very much explained every each and every detail of all the concepts there. If you are not clear with the concepts, I would highly recommend you to rewatch the videos again and again, and keep on writing simultaneously, and keep on doing the questions along with the topics we are covering. So keep on doing the hard work. Stay positive. All the best. Thank you.